Yeah. There's people. Uh-oh. Ah, there we go. What's going on? Hmm, that's a little awkward. There we goes. Yay. Okay, that connection's got to be loose or something. That's not a good sign. All right. Happy Thursday. So just a reminder, we have our midterm coming next week. So like I said, we'll do review on Tuesday. While I'm thinking about it, right, we do have a regular quiz. So it'd be chapter 15. But I was kind of debating, and I'll take your opinion right now, what to do with the chapter 16 quiz. So I've printed it out for you guys. So at the very least, I was thinking you can take it home and study it. I'm just not sure if you all wanted it to be another quiz grade, like a take-home quiz, collaborative quiz, or something, homework, or just like throw it out and use it as review and like study. extra, extra credit doesn't help. That's what you guys don't understand. If you curve everything, collaborative. Yeah, I mean, we could do like, yeah, I mean, I have several thoughts. Like, we could also do like the two quizzes, so 15 and 16 as like collaborative practice. And then we could do like grading on Tuesday and like have that be easy, like completion grade. Like I'm just kind of throwing out ideas, but I just wanted you to see quiz 15 and 16 so you could study. Otherwise, you're not going to have 16 to study for, and we may not do a chapter 16 quiz otherwise, right? Because we got the midterm. Yeah. Yeah, I mean, we can review it on Tuesday if that sounds good. So maybe we'll do that. I'll hand out the quizzes for quiz period, and I'll make them collaborative so you guys can work, study, and we'll just kind of hone in on what we don't know so that we feel really good for the midterm. And then, yeah, we'll just take it as a completion, probably grade or something. And all right, I like that plan as long as everyone's on board. So we'll do that for our quiz. All right, so let's finish up. So like I said, we'll finish up the chapter, and then we'll go back and we'll do the math that we need for the lab. And it'll give us a preview to kind of the last half of this quarter and the first half of third quarter. All right, so the last little bit is like soda canning. And so, right, this is basically, well, how do you can something and pressurize our soda? And so this is another one of those, unfortunately, that just kind of depends on this gas constant. And so it tells us, and I feel like we've discussed this before. Maybe we haven't. Here we go. This is what I was thinking of. And so kind of the problem with gases and what's kind of opposite from what we think about is that our gases actually tend to have a lower solubility in water than ionic or polar covalent. And so, right, it's kind of opposite. So that means when the temperature, right, is lower, then our gas is more soluble. And sorry, I need to fix my Wacom mapping. Oh. Okay, it should be okay. All right, so then, yeah, as a gas, it is, again, more soluble at cold. So that is opposite, right? And so part of that is because gases tend to be non-polar for the most part, at least most of the gases that we think of, right? Nitrogen, methane. Right, so usually they use like either nitrogen or CO2 for bottling, just starting to think of drinks. And so both of those, like I mentioned, are nonpolar. And so then looking at how to pressurize and can your liquid. So of course, right, the larger the partial pressure of the gas in contact with the liquid, the more soluble the gas is in the liquid. So just trying to force those gas particles into the liquid. And so like I mentioned, unfortunately, this is just dependent on one of those gas law constants, right? We've kind of seen that a lot in this chapter. Is like you have to look up this certain constant. So if you were to be given this on an exam, right, I would provide you, there's a gas, and then again, right, each gas has a Henry's law constant. And then typically, we may see these units. So these are the most commonly used units, molarity per ATM. But as usual, right, be aware, check your constant, make sure that the units match and that it cancels out appropriately with your pressure. So again, given that our KH is in ATM, that means our pressure should match in ATM as well. And then again, right, highlight this because this is opposite of solids. So I'll put that again, opposite of solids. And so, right, if we recall, so generally speaking, you add more kinetic energy, that gets things more solubilized. So that only applies for solids. So again, with gases, right, that makes it much less soluble, and then the gases start escaping. And so some of that you can see for yourself if you've ever like opened up a cold soda and poured it out, right, one that's been in the fridge versus a warm soda. So you would notice, right, the warm soda kind of has that more like bubbly, fizzy effect since all the gas is escaping right as soon as you open it. Something else you could do if you're ever like bored enough with your soda cans, right, you have your soda can under pressure, and you know you have that little ridge on your soda can where you like pop the tab. If you just like gently rub that for a while, eventually it'll break, right? Because the whole thing's under pressure. So if you just stress it out a little, you should be able to pop your soda can that way. And then, so like we were looking at, so how can we make our solvent hold more solute? And again, that goes back to our Henry's law constant. So of course, part of it is we can just add more pressure, right? And or we can also, right, vary the temperature. So we've kind of seen that. And then other things, I realized I didn't pull up any videos on this, but you can always kind of look at these saturated and supersaturated solutions. Actually, let me try to find one. So let's think about what this is kind of referring to. So, oops, sorry, my Wacom still isn't mapped correctly for some reason. Come on. So are you guys familiar with like the Mentos and diet soda thing? And so that's kind of part of what this is. And so kind of thinking about what happens when you put the Mentos in the diet soda. So it basically, right, disrupts our saturated solution. So, right, we have a saturated gaseous solution. And then our Mentos just provides a spot for like nucleation. And then once you get that nucleation, it disturbs your whole system, right? That's why it totally bursts out and disrupts. And then, of course, there could be like additional effects. So why they always pick diet soda is, I think, like the aspartame or something just provides extra nucleation effects and makes it more explosive and fizzy faster. And so you can see all sorts of videos of people playing with that, right? Trying to shake carbonated beverages and exploding them and all sorts of things. And again, you're just creating instability so that it separates right away, right? So that you're immediately off-gassing. All right, so let's look at this. So now, and I'll have to give you our Henry's law constant. So what pressure of carbon dioxide is required to maintain our carbon dioxide concentration in our club soda at 0.12 molar? And then So looking up, I'll just copy this table down. So again, on an exam, I'll provide you these should you need them. So what do we get for this one? So right, not too bad here. You really don't even need to look at the formula, right? The Henry's law constant basically gives you everything we need. So we see we have to multiply by our pressure to give us how much we want to be solubilized. So 0.12 molarity is equal to, again, we need our pressure and then our constant, so 3.4 times 10 to the negative 2. And so now we can just plug that into our calculator, and if you're online, you can type it in. So say hi if you're online. Otherwise, you can yell at me once we get our answer. So let me know if you got the same thing. So I see chat got that. Do we get that in here? So I see some yeses. So again, right, that means we just have to bottle under 3.53 ATM then. All right, questions about that? I think that's the chapter. So pull up your homework, but before we look at homework, let's jump to our lab. So you might want to look at your pre-lab. So if I do the pre-lab for you guys, I think you can do the post, because it'll be the exact same process. So I'll let y'all get out your labs. All right, so now we need to do a little bit of background to understand what we're doing. And so let's look at some background first. And so what's going on here is, right, well, we want to find the pH of citric acid. However, there's a slight problem. And so let's look at pH. So again, we haven't gotten there. We switched the labs around so that the kinetics lab would pair better, but then that kind of left the titration one in an odd spot, so hence why I stuck it here. And so our quick introduction to pH. So we have strong acids, such as HCl or nitric acid, and these fully dissociate. And so that means, right, if we have 1 molar of HCl, it dissociates into 1 mole of H plus ions in solution, And then I don't think we covered acids and bases in here. I'm sorry, I get mixed up sometimes. But then we would take the negative log of our H plus concentration, and that gives us our pH. So that's relatively simple, right, for our strong acid case. And so then the problem is, well, what happens when we have a weak acid? What does that mean? And so a weak acid, so it does not fully dissociate. So that means there's some sort of equilibrium. So that's what's kind of teased down here. And so the setup is pretty nice, but like I said, let's look at a little bit more. And so that means we're looking at some sort of equilibrium. And now this is HA, right? So like our protonated acid. So this would be like a monoprotic acid. And then we can disassociate it. And then we get some sort of concentration of H plus, and then A minus, which is just our conjugate base salt. And so then this is defined as Ka. So this is called, right, our equilibrium constant. So again, this is just, right, our mathematical expression of this relationship, right, of this ratio. So however, whatever the concentration of H plus is times A minus all over whatever is left associated, right? And that gives us our Ka value. And so every weak acid has a specific Ka value. And so you could look this up, or eventually when we get to this chapter, you'll have a table of more of these, but Google is fine. You will find small discrepancies in these, but it shouldn't matter that much. And okay, well now we're ready to at least try to understand what's going on, and then we'll do the math and solve this problem. So okay, we want to find our pH, which means that we need to figure out how much H plus is actually disassociated. And so the best way to do this, and like I said, we're going to be doing a ton of these, probably starting right after the midterm and then going to next quarter and continuing. But these are called ICE diagrams, or I actually call them RICE. So I grew up in Texas, so I have some connections to Rice University, and of course they're going to call it a RICE table, which works a little better because we have R for reaction here, so that's our setup. Okay, and then this is kind of relevant. So we're only considering the first disassociation. So, right, we only care about the first H plus. We'll get into subsequent disassociations later in the acid chapter. I want to say third quarter if I remember correctly. And so what we're saying is, okay, let's start with our 0.150 molar solution, right? So this is our kind of initial conditions. And so that's what's set up here. And then it's saying like, okay, pretend that nothing has disassociated yet, right? So that's why we have 0, 0. If we could just like magically pause this, like, okay, they have not disassociated, so we have 0 of each species. And then the change is our disassociation, or later on it could be like a reaction or something, right, if we're trying to titrate. So we'll get into, again, all that later. But for right now, we're just saying, okay, it's going to disassociate into some equivalence, right? So it's going to make X amount of hydrogen, X amount of our conjugate base, and then subtract that same amount, right, from our original. And then the important part is this equilibrium expression, right? Because this is what we're going to plug in to our Ka. And so I'll just kind of rewrite it so we're all explicit right now. So 7.14 times 10 to the negative 4, since that's, again, our Ka for citric acid, is equal to, I'm just going to rewrite our general expression. So it was however much is disassociated times our conjugate base all over what is still left associated, which is then equal to, and now I'm going to, well, I guess I won't get too excited. So x times x, and then overwrite our equilibrium, so 0.15, again for our original molarity, minus x. So does that make sense so far? And then, so at this point, it's just algebra. So now we can just do algebra. So equals x squared over 0.15 minus x. And so this might end up being a quadratic equation. So now, right, this algebra. So now, good time to practice your math skills. So I'm just kind of writing it out. Oops. So then probably plug it into the quadratic formula is what I would do. So x squared, now plus 7.41 times 10 to the negative 4x minus 1.115 times 10 to the negative 4th equals 0. And double check my math. It's just all algebra. And then do we remember our quadratic formula? Yeah, excellent. Yeah. Yeah, I mean, that's the beauty of repetition. So yeah, write that down if you don't have it. I mean, obviously we're not going to be tested on it right this second. It's just helpful for the lab. And so now we can plug it in. So write A, B, C if we remember, don't remember. And so again, just help me double check my math. Easy to mess up. So I'll probably try to calculate what's under the square root sign. So I just solved for what was under the square root. That's what I got. Again, double check my numbers. And then so what you'll notice is, well, we can't subtract that, right? That's going to give us a negative number. We can't have a negative pH. So we have to add. Again, just double check my math for me. So plus this answer. So about 0.02 for our x. So right, that's again our H plus concentration. And so now we can plug this in to get our pH. So negative log of about 0.02 roughly. Oh, you're fine, yeah. And so double check me. Again, this is this will be a tedious chapter, but I mean, at least we don't do calculus in here. Trying to be optimistic. Yeah, see, like we're not in physics. So double check. Did we get this answer? Oh, I think I screwed up. Sorry, I just realized something. I didn't divide it by 2a. So I could be wrong. So yeah, I forgot to divide by 2. Sorry, negative log of this answer. So I get 1.99. Sorry, messed that up. So yeah, again, double check my math. So you see I made a small error, so I forgot to divide by 2. So I think chat had it, I thought, of 1.99. Did we get that? Do we agree? Just make sure you... Yeah, it's totally easy to make a mistake on these. All right, that look good. Yeah, so I think you guys caught my error. So excellent. I think we're all getting that. So did we all get that? I just want to make sure. I don't want to rush anybody. Yeah. Oops, if I can. There we go. And yeah, so I think the correct answer should have been 0.01018 molarity from the quadratic, right? And then plug that into our log to get our pH. Everybody follow, not follow? So yeah, so if you've done the lab, it might be advantageous for you to like do that in here during our we'll call it our quiz period, but I feel like at this point it's our catch-up period for anything we need to catch up on. Okay, are we okay with this? Do we need to see anything again? Okay, speak now. Yeah, so that's your B, right? And then did you get this? 0.02113117. So technically you want to test both, but then, right, if you do the subtraction, they'll give you a negative number, so that's where you toss it out. But that being said, yeah, make sure you test every value, because there will be other cases where, like, both the negative and the positive will give you positive numbers, right? So, like, if you do the subtraction and you do the addition, they're both positive. So then you have to, like, retest it with your condition, or, like, maybe one won't make sense or something like that. Potentially to the original, or like double check the original conditions and stuff is what I'm saying. Make sure that you don't get anything unreasonable. Since right, that's the inherent mathematical problem with the quadratic is you get two answers, but we should only physically have one. So only one will make sense. And yeah, generally, like I stated, it's the subtraction one, because generally that gives you a negative, But yeah, like I said, this will be a good teaser for later, so we'll do this many more times. All right, so I did want to at least briefly look at the homework with the Van Hoff factor. All that. And so what's the trick for this one, right? Because you have on the back of your first page, right, you have all the rankings of solutions. So it starts with 6, but then it wants you to rank it like in order of increasing vapor pressure, increasing boiling point, blah, blah, blah. But before you get wrapped up in like trying to rank them, what's the first thing you have to do? And I mean, it kind of tells you, because it tells you, right, determine your ideal Van Hoff factor. And then what does that mean, right? So then what do we need to kind of change to compare them? Yeah. Sorry. Yeah, chapter 16, homework. So looking at how to rank those solutions. Yeah, but then, so what do we need to do? Like, I don't want to give away the answer quite yet. But, so what do you notice about sucrose? Does it disassociate or not? So no, right? So then it's still effectively a 0.1 molar solution. But then what's our Van Hoff for sodium chloride? And then what does that make the effective molarity? So 2, so doubling, good. And so I'll put right times 2. So that means now it's a 0.16 effective molar solution, right? Because we're talking about of ions. I'll add that, ions. And then what about magnesium chloride? So times 3, so 0.09, excellent. And so now we can effectively rank them, right? And so now let's do this. So who has the highest osmotic pressure then? So sodium chloride, since it has, again, the greatest number. And then sucrose is always going to be in the middle of these orderings. And then magnesium chloride for this one. And so that should help you with the rest of them. So we could practice. So 7, just ask for then vapor pressure. So which solution has the highest vapor pressure? Check it again though, because remember vapor pressure, boiling point elevation. So what does the ions do? So yeah, we just got to flip the order then, right? So yeah, so magnesium chloride then has the highest vapor pressure, right? Since it has the least amount of particles. And then it becomes pretty easy once you have this ranking correctly. And then again, they'll always stay in the order, is just flipping them. And so we'll at least do boiling point. So then which one would have the greatest boiling point? Yeah, so that would be the sodium chloride, and that goes, again, back to our great pasta water debate. So sodium chloride, sucrose, and magnesium chloride. Yeah, see, so that's the thing that I'm curious. Like, are you supposed to cook it longer, lower, or like higher, shorter? Like, which is optimal there? Yeah, so and then someone brought up like it might depend on the pasta, right? Like too, like thickness, thinness. Yeah, there's a lot of yeah, fresh, dehydrated. So good. Oh yeah, let's do this one. I forget that these are tricky. Actually, let me see. I think I had a problem in my notes that we didn't do. So let's try this one. This will be a good practice. All right, so we have the osmotic pressure of a solution containing 5.87 milligrams of an unknown protein per 10 mils of solution is 2.45 torr at 25 degrees Celsius. So find the molar mass of the protein. So how is this one coming? I know people in the chat, we kind of had the formula going of our osmotic pressure. And I like to put the Van Hoff factor in there just so I don't forget. But I, molarity RT. So do we all kind of start there at least? But then what were some issues? What do we have to do before we get too excited? Excellent. So yeah, they try to trick you. So 2.45 divided by 760. So that gives us in ATM. And remember, we have to be in ATM because of the gas constant, so that's what's dictating that. All right, so then we have our pressure. So now we can start setting up our equation. So, right, we're trying to solve, well, first we need to find molarity, right? And so we need to get to molarity. Once we figure out our molarity, we can go from there, right? Get moles and figure out what this corresponds to. So let's just start plugging that in. So 0.0032323 ATM is equal to our molarity times our gas constant, 0.0821, times our temperature. And then what do we need to do with our temperature? So convert to Kelvin, so 273 plus 25. All right, so now let's solve for molarity. And so that's what I get for molarity. So just double check my number there. So 1.317 times 10 to the negative fourth. And so now, right, molarity is equal to moles over liters then. And so we have, right, so 0.01 liters. We can figure out how many moles that is that we have, right? So times 0.01. So converting, right, our milliliters to liters. And so now we're given moles. And so now the last step is we can find, right, our molar mass. So some sort of proportion or divide. I'll set up a proportion just for fun. So we have 5.87 milligrams, right, was equivalent to 1.317 times 10 to the negative 6. And so now let's figure out for 1 mole. So cross multiply. And so let's convert this. I don't want to be in milligrams, right? Otherwise I'll get my mass in milligrams. So let's convert this to, so 0.00587. And so now we can divide. So 0.00587 divided by my answer here. And so that gives us our molar mass. And so, right, pretty large, but I believe it said it was a protein. So it makes sense that it would be large. And double check our sig figs, so 3 sig figs. So about 4,450 grams per mole then. And I guess we could have rounded up to 60 as well. Questions about that one? No, you're fine. We can.
It's just at the very end. I just didn't know. Did you write down all the math for like the last step before your answer? I think I need to see that because I wasn't able to listen because I was still writing other stuff.
Yeah, so let's see. So we solve for molarity, right? So we solve for it here. Sorry. And then I said, well, how many moles do we have? Because we were given only 10 milliliters, right? So that's why I took the 0.00587 times 0.01 liters, right, to give us moles. And so that's how I got that number there.
So it's just
Or sorry.
M equals N over V, but then you just did M divided by V.
Yeah.
Or you multiply by it?
Sorry, yeah. Oops. I don't know what I did. Sorry, this was the molarity. And then I multiplied this by 0.02. Sorry, I forgot. I got lost in my own math rereading it. So yeah, you solve for the molarity, you get 1.317 times 10 to the negative fourth. Then multiply it by your liters. So multiply it by that by 0.01 liter to give you that. Does that make sense? So yeah, just check that out. So these are pretty tricky, but you'll probably have one of these on the exam, but it shouldn't be too bad. Just watch the units on everything. All right, any other questions or anything? Anything that we want to touch on from the homework? All right, should we do our quiz then? Is that quiz time then? All right, so I'll hand out the quiz. Yeah, online. If you have any more questions, just let me know. I'll hang out for a second. While y'all are thinking of any more questions, I'll hand out the exam. So if you're online, just send me an email and I can send you the copy of both the quizzes. So like I said, the consensus is I think we're going to just do take-home review, and then we'll turn them in next Tuesday more for a completion grade. So you guys can study. So let me just get 15 out first so I don't mix up all my papers. And then I'll get and you make it extra. So yeah, lab makeups we can do during finals week if you can't come. I mean, not finals week, next week, midterm week. Did you get a quiz? Chapter 15? Yeah. So yeah, makeups for lab, let's schedule them for next week. So there's no official lab. And then I'll hand out 16 as well. And then I'd probably at least try it on your own, and then you can start pulling your neighbors for help. But yeah, so they will both be take home, even though only one says take home. But we'll just do them both take home, review, right? Get your mind ready for the exam. So it'll be a mix of multiple choice and free response. You guys got 16. Did you get 16? Okay, perfect. All right, I'll leave copies in case somebody missed one. All right, then I'm going to stop the stream.